My name is Krishnendu Chaudhary, aka Krish, and I am the author of the book Math and Architectures of Deep Learning from Manning Publications of New York. And today I'm going to talk to you about PCA, Principal Component Analysis, SVD, Singular Value Decomposition, and Latent Semantic Analysis, LSA. So first, a little bit about myself. I am currently the CTO and co-founder of Drishti Technologies of Palo Alto, Silicon Valley, California. I am glad to let you know that my company, Drishti, has been recognized by Forbes magazine as one of the top 50 AI companies of USA. Before Drishti, I was with Google for like a decade, and I have worked in multiple departments, mostly Google Research, Google Photos. I actually founded, more or less, started the Google Newspaper Search and also led the Google News Archive for some time. Other than that, I have worked at Adobe Systems San Jose with their Advanced Technology Group, which was basically the research, and also for their Advanced Development Group for another 10 years. So you can say I have been around, which should be apparent from my gray hairs. Before we take a deep dive into the topic of the day, I would like to actually tell you about kind of an article of belief with me. I would say deep learning and indeed machine learning is just a form of high dimensional geometry. Basically, we represent any input as an array of numbers. An array of numbers can be thought of as a vector, and a vector is essentially a point in a high dimensional space. The number of dimensions is same as length of the vector, length of the array. Here is the crux of it. The set of interesting points usually forms a very small cluster, a pattern in that large space. All of machine learning is basically trying to identify that pattern, discern that pattern in this distribution of points, which corresponds to a distribution of points. Let's take a quick example. We will examine this in more detail later. But let's say we are trying to identify images of zebras. Now, an image is representable like a vector. Basically, the vector elements of the vector would be the pixel color values. So we have a vector representing an image. Now, zebras do not have arbitrary color, right? They have a very specific color pattern. So the images that contain zebras would actually be a very well-defined, reasonably well-defined cluster of points in that space of colors. If we can identify that subspace, that region which corresponds to zebras, given any new input array, we could tell whether it belongs to that subregion or not, and based on the answer to that, we can say whether the photo is that of a zebra or not. This is a very crucial idea. It may seem obvious to some of us, but I feel it's very important to identify this. Let us actually look at a toy example, which is represented in this. Now focus on this. In this toy example, like I said, most of real life machine learning deals with hundreds or thousands of dimensions, but this is a special toy example where we are dealing in only 2 dimensions. Now, let's say the points of interest are shown by these black dots. These are our zebra images, whereas this 2-dimensional plane is set of all possible images. Of this, the zebra images, let's say, are forming this cluster, which looks like a long and narrow ellipse. How do we identify the pattern here? Well, the very first thing we note is that the distribution is such that the spread of the points is mostly along this thick line here, the one on which I'm moving my mouse right now, indicated by the thicker. There is some spread variation along this thinner, along the perpendicular direction, but it's significantly less. What that tells us is that we can actually probably represent this entire set of points. We can replace this with this single straight line. In other words, we can project them. The empty circles, the hollow circles actually represent the projected points. And then we can essentially replace this cluster of points with a single line. That is kind of a pattern recognition. We have identified the entire pattern of zebras, let's say, with that line. So we can say if my point lies near about that, my query point lies near that, it's a zebra. What does this really buy for us? Well, in some sense, this is a little bit like big picture formation in our heads. When a soccer coach is looking, the soccer coach is looking from outside the field, and the soccer coach is seeing the whole game. The coach is not seeing too much details, but getting a big picture of the game. A player with the ball is seeing a lot more detail, but is lacking the big picture. Consequently, it's easier for the soccer coach to actually analyze the game better. A very similar thing is happening here. We are getting rid of these small variations, which you can think of as details, and we are getting the big picture that most of the distribution is along this line. As a result, this simplification might help us to do a better analysis of the points. And of course, we have created a more compact representation which takes less space. That itself is a win. So as a result, this trick, which is known as dimensionality reduction because this was a two-dimensional distribution of points, for instance, we have reduced it to a single line, which is to say a one-dimensional entity. That is why it's called dimensionality reduction. This facilitates big picture analysis and also creates a simpler representation, simpler and more compact and less expensive representation. So that, in some sense, is the core idea behind principal component analysis. We will get into more details very soon, but I just wanted to leave you with a synopsis of what we are going to do in this session right at the beginning. Let's now try to look at a real life problem. Although we will look at a toy version of a real life problem, but it is a real life problem nonetheless. That real life problem is document retrieval. Let's say we have a set of documents. In this little example, we have only 7 documents, D0 through D6, and each document is very small, a few words. However, this is still a valid example. And the problem is we will get a new document and we will have to retrieve documents from our library of documents in order of similarity. That is, the most similar document should be ranked first, the next closest document should be ranked second, and so forth. You can easily imagine where this is very important. Google, for instance, would need to solve this problem constantly, meaning this is their bread and butter. The technique I'm going to discuss right now is not the only thing Google does. It's a simplified version, but still, this problem is extremely important for Google. What do we do at this stage? You might have realized that the problem essentially boils down to estimating similarity of a pair of documents. If we solve that, we have solved everything in this document retrieval. So given a pair of documents, we have to come up with a quantitative way of scoring their similarity. The very first thing to do is to have a quantitative representation of the documents itself. This we do with a trick called term frequency. Essentially, we imagine a very long vector. This vector's length is same as our vocabulary's length. That is, every word in our vocabulary has a specific slot in this vector. So if we go by dictionary ordering, the first slot may correspond to aardvark or something, and the last slot will probably correspond to a word like zymos, starting with a Z. In the middle, we will have all other words in our dictionary. So what we do is we go into the document for, let's say, how many times aardvark appears in this document? 0. So we will enter a 0 next to aardvark. How many times zymos appears in this document? 0. However, we will enter 2 next to roses because rose appears twice in this document, and so we will create a vector corresponding to every document. So this table shows such a vector from those 7 documents that you will notice that roses we have a 2, and just to simplify, we are kind of pretending that our dictionary has only 4 words. I told you this is a toy example. Then gun appears once in document 1 and violence appears 1. You will see a score of 1 against each of this, and the word America also appears once, and hence we have a score of 1 against America, and so forth. So each row is a document turn frequency vector. This is as good as any other way. This is a pretty good way to actually create a document descriptor vector, so to say. One thing to be noted here is we are not paying attention to ordering or sequence of words. This is a so-called bag of words model. We are just, if a word appears anywhere, it cannot distinguish between words appearing in one sequence versus another. It just counts the number of occurrences of each word. Anyway, that's not a bad way. May not be the most sophisticated, but not a bad way to describe a document. This bag of, so we will work with this term frequency bag of words model. Now, how the geometric view corresponding to this is shown here. What you will notice is each word is corresponding to a separate axis, and the number of the coordinate corresponding to that axis is the number of occurrences of the word. And this way we will get a value for each coordinate, and by combining all of them, each of these points is corresponding to a single document. There is one specific property deliberately created, so is that in most of the documents the word gun and violence appears the same number of times. Here there gun once, violence once, here gun twice, violence twice, and so forth. Excepting D5 and D6, in D5 only gun appears, in D6 only violence appears. Keep this in mind. This is going to be somewhat crucial to understanding what we are going to say very soon. We have this geometric representation of the document vectors, the 7 document vectors. There are 7 points, each corresponding to a separate document. This is the geometric representation. Now, how do we measure similarities of a pair of documents? Well, each document is a point, or in other words, it's a vector. There is a very well-known way of measuring similarities between a pair of vectors, namely the dot product. So we can use that. That measure is known as cosine similarity. Of course, if we just take the dot product, then longer documents will have an unfair advantage. They will always, long documents would always score higher than very similar but smaller documents. We want to normalize against the document length. That is why we divide the dot product by the length of the 2 vectors. This is called cosine similarity. We can use this, and most of the time it works, but it has a very specific blindness. In some sense, the idea of PCA evolved to cover that blindness. That is why I'm starting with the simpler technique of cosine similarity and pointing out where it fails. We will later show how PCA covers that blind spot. In order to understand that, let's go back to our list of documents. If I take the dot product or the cosine similarity between D1 and D2, I will be okay. But watch what happens if I try to take a cosine similarity between D5 and D6. The cosine similarity will be 0 because there is no common word. That is a mistake. If we examine the entire set of documents, it's quite clear that the word gun and violence occur together most of the time. There must be some kind of semantic similarity that is not visible to cosine similarity because it's only looking at common words. It's not looking at secondary relationships like that. This is what PCA addresses. So in PCA, we will very soon see that that problem is mitigated.